right, let's finish up fat characterization today, and hopefully we get time to start protein separation and characterization. Okay, so just to bring you back to where we left off last time, what is saponification value used for? So when I ask in an exam, define saponification value and what it's used for. So what would you say? Let's see if anybody's going to respond, or maybe have a moment to look back and review what is saponification value for. Coleman? Yes, it is the index for the average molecular weight of fatty acids or triglycerides of that oil. So it's used as a kind of an identification value. It's very characteristic for different types of oils. And the value we get is used to calculate the average molecular weight of triglycerides and the average molecular weight of free fatty acids, not free, sorry, of average molecular weight of fatty acids of that particular oil. And yes, Abby, it's the milligram of KOH to saponify 1 gram of sample. It's very important for you to state that unit. Knowing that unit helps you remember the equation, helps you remember what goes in the denominator, what do you multiply by, what do you use in the equation. You really need to know the units, what it is, milligrams of KOH needed to saponify 1 gram of sample. Very good. If oil A has higher saponification value than B, which one has lower average fatty acid molecular weight? Now, for you to know this and to come naturally to you, you really have to remember your chemical reaction. You really have to remember that you have 1 mole of triglyceride reacting with 3 moles of KOH. Okay, then it gives you glycerol and salts of fat, fatty acid, salt, 3. Okay, so you really need to remember this end of the equation of the chemical reaction. 1 mole of triglyceride reacting with 3 moles of KOH, and you got to remember if it is, let's say, 0.19, the example that I gave you last time, 0.19 grams or 190 milligrams reacting with 1 gram of triglycerides. Okay, so the larger the molecular weight, okay, there will be less number of moles in 1 gram of sample, all right? The larger the molecular weight, there will be less of it in one gram. Then the value here will be lower. So that's what you want to remember. You want to remember it's an opposite relationship, right? The larger the molecular weight, the less number of moles they're going to be, then the less KOH will react with these number of moles. Okay? Chemical reaction, balancing chemical reactions there. Okay, and knowing that when you have large molecule, less of them will be in 1 gram versus smaller molecules, there will be more molecules in 1 gram. Okay, the more molecules you have, the more KOH needed to saponify these molecules. So the larger the saponification value, that means you have more molecules of triglycerides. That means you have more molecules of triglycerides in 1 gram of sample. Okay, just think about it for a little bit. Repeat, pause, and repeat the recording so that it kind of clicks in your mind what I'm talking about here. Also, the equation that we used, we had 3 times 56.1, which is the molecular weight of KOH, times 1 divided by 0.19 grams, if you remember. So this value here, the larger this value, the lower is this X here. The larger the value on the bottom, the lower the X. which is the molecular weight of the triglycerides. The smaller this value in the denominator, the larger is your x. Okay, so it's an inverse relationship. So remember it whichever way is easier for you to remember. All right. Which test is used when testing efficiency of hydrogenation? Iodine value. There we go. Yes, so iodine value is a measure of degree of unsaturation. The hydrogenation is we are saturating the double bonds, and when we saturate the double bond, the iodine value should go down. Presence of free fatty acids is an indication of what? It has multiple indications. What could it be? Hydrolytic rancidity is one. Not refined oil is another. There's one more. Frying oil, age of the frying oil. Yes. Okay, name few physical characterization tests. Just a couple that we talked about last time. Physical characteristics. Tushan? Melting point, yes. Jean, did you want to say anything? Refractive index. So melting point, refractive index. What else? Anybody remembers more? The what? The smoke point, the spark point, the fire point, the cloud point, and I don't know what else there is. But these are all physical characteristics of the oil or fat. All right, so here's where we stopped last time. We didn't get to the oxidative rancidity or measuring the current or present status, oxidative status of the oil. So let me put this. So measuring lipid oxidation, we're going to looking at the current status so there's the current status and measuring oxidation over time to determine the shelf life. So to measure the current status, we do peroxide value on the oil that we have. So peroxide value, it measures peroxides, which are the primary products of oxidation. So it is defined as milliequivalents of peroxides per 1 kilogram of sample. So that is the definition. So remember the units, milliequivalent of peroxide per 1 kilogram of sample. So because we're looking at milliequivalent, so it's volume times normality. There is no molecular weight of anything here in this equation. So again, if you remember the unit, you remember your equation, which is the volume times the normality. There is no multiplication by molecular weight. So it's not, we're not looking at mass. We're not saying milligrams or grams of anything. So we do not multiply by molecular weight of anything. So, and per 1,000 grams or per kilogram of sample. So therefore we divide by the weight of the sample and we multiply by 1,000 because 1,000 grams, 1 kilogram. So this is how you need to remember the equation. If you remember the units, you remember the equation. Again, you have to know how to derive these equations, and we derived them in class for the protein or calculation of percent nitrogen. So it follows the same concept. But then when you know the unit, you will know when you need to divide by 1,000 or not. We're not dividing by 1,000 because we're looking at milliequivalent. So milliliters do not have to be converted to liters. So we do not divide by 1,000. So milliequivalent per kilogram. So we divide by the weight and we don't multiply by 100, we multiply by 1,000. So if you remember the unit, you will remember what goes in your equation. Okay, So a freshly refined oil. So we don't have free fatty acid. Hopefully you refine the oil so the free fatty acid level is low and it is fresh, so the oxidation did not yet start. Will have a peroxide value of 0. How about a very rancid oil? What do you expect the peroxide value to be? A very rancid oil. Do you expect it to be what? Yes, Colin. Very late stage, the very end, low or 0. Why? Because peroxides are the primary oxidation products. So we start low, we start at 0. If very fresh and hardly any free fatty acids, we start at 0. And then you, over time, or if the sample was exposed to oxygen or heat, what happens is your peroxide value starts going up. At the same time, secondary metabolites are going to start to occur. So the peroxides will start converting to secondary metabolite. So at some point, the rate of the conversion of peroxides to secondary metabolite will be higher than the rate of formation of peroxide, because all of the oil at some point will be oxidized. So then you go for a bell shape. You start at 0, you go up, you reach at the top the maximum peroxide number or value, and then it starts going down. As it's going down, that means the rate of disappearance of peroxides is higher than the rate of appearance of peroxide until there's no more peroxide formed and everything is converted to secondary metabolite. You go back to 0. So how do I know if I measure an oil peroxide value of an oil and it's 0, how do I know if it's very oxidized or if it is fresh? What would be an easy indication? Smell it. Yes, Chris. Yes. All it takes is smell the oil. It's going to smell really bad if you get peroxide value, but it smells really bad. That means it's fully oxidized. Or you can do another test, which would be a secondary metabolite test, which we often do because sometimes it smells, but not too bad, but you want to know exactly how oxidized. You can't just base it on the smell. So you want to determine primary and secondary oxidation product, and that's what we will be looking at in a minute here. So back to peroxide value, the reaction or the chemical reaction that we do is you have the peroxide, you react it with potassium iodide, you get iodine. The iodine in presence of starch indicator will be blue. We titrate with sodium thiosulfate and we until colorless, until all of the iodine has been titrated with sodium thiosulfate. No, the last drop will render everything colorless. So in this case, we have sample minus blank. If we run a blank, the blank shouldn't have any peroxide in it. So there shouldn't be much of any iodine produced. Then you would have theoretically a blank of 0 for peroxide value or close to 0. So the sample minus blank in this case. So anisidine value, it measures degree or amount of unsaturated aldehydes. So aldehydes are secondary oxidative products. So anisidine value is basically reagent, is anisidine reagent, reacts with unsaturated aldehydes. These, upon this reaction, a chromogen is formed and you measure absorption at 350 nanometers. So if you have anisidine value and you have peroxide value, you can get something called Totox value. The Totox value is basically the anisidine value plus 2 times peroxide value. And there are tables for these values. So if you have a fresh soybean oil, has an anestin value of less than 2 and a Totox value of less than 4. Hexanal is another secondary metabolite of oxidation, and it's commonly measured. So if we're looking at the oxidative shelf life of grain flour, for example, a particular grain flour, it's always a good thing to have one measurement for primary oxidation over time and one other measurement for secondary oxidation over time. So it's very common. We do that also a lot in the lab when we look at the shelf life stability of a grain or a particular flour. We measure hexanal and we measure peroxide. So hexanal is easy to measure because it's volatile. So we have our sample, we put it in a sample compartment for a certain period of time, and the headspace is where hexanal will be, which is a volatile. So the headspace meaning the space above the sample in the sample compartment. So we just insert our syringe in the headspace and take out a certain volume of the headspace or whatever is above the sample. And we measure this by GCFID, and we can determine the amount of hexanal. Obviously, we need standard, and we can quantitate hexanal or other compounds that are commonly measured as well as are pentane, pentanal as well. They're also volatile. The measurements of hexanal, it correlates well with sensory evaluation because it correlates with the sniffing perception of the sample. The good news about it is you don't need to extract the fat. With peroxide, you need to extract the fat in order to determine peroxide value. With this, you don't have to extract the fat. You just, because it's volatile, you just measure the amount in the headspace. This is a very common assay for secondary metabolites. We call it T-bars. So T-bars stand for thiobarbituric acid reactive substances, T-bars. So it is a test specific for malonaldehyde. And malonaldehyde is a secondary metabolite for linolenic acid specifically. So if you have an oil that is high in linolenic acid, that's a good indicator for oxidation of that oil. So it's very common for meat products to be assessed using T-bars the lipid oxidation of these products to be assessed by T-bars. And it's very simple. It's based on reaction with thiobarbituric acid. And the thiobarbituric acid reacts with malonaldehyde to give you a chromogen or a color or a compound that absorbs color. And it's measured, the absorption is measured at 530 nanometer. It also correlates well with sensory evaluation and peroxide value. But it has a disadvantage that malonaldehyde is a reactive substance still and can oxidize other substances. And instead of interacting with TBA, would already interact with other substances, and then you would have an underestimation. Other than measuring malonaldehyde using the T-bar assay, we can do HPLC determination or using liquid chromatography to determine the amount of malonaldehyde and other aldehydes as well. Now, this is an important section here to look at oxidative stability over time. So this is to assess shelf life of your oils, but it's a very common method used to assess the effectiveness of antioxidants that are added to the food. So looking at natural antioxidants versus synthetic antioxidant or a new antioxidant. So it's a very common method to determine the effectiveness and how the shelf life would extend when you have a specific antioxidant in there. So we determine what is called induction period. The induction period, basically, if you look at this graph here. So in this graph, you have the time on the x-axis and an assay to monitor lipid oxidation. Oftentimes, you can monitor oxidation of a very fresh oil by generation of peroxides. That's simple, easy method. So the induction period basically is the time before until we see a significant increase in oxidation. So going from 0 to a certain amount that is considered significant for oxidation. So that's the induction period, the time before a sample starts oxidizing. So this method, the monitoring oxidation over time, allows us to determine the induction period. And also it allows us to determine the shelf life of the oil or fat and the effectiveness of antioxidants. The way we determine induction period is really using accelerated shelf life studies. So instead of storing the oil and monitoring it over months and having that being tedious and lengthy time of analysis, we try to do it faster in a way that we want to get kind of an idea or an estimate fast. So we do three different types of methods. First one is the most common one, which is the oven storage method. You just take the oil, you store it at 60 degrees C, 60 to 80 degrees C, along these lines, and you take samples out at certain time points and you measure peroxide, say. And then you plot until you get such a curve. And you can determine the induction period. Very simple, very commonly used method for determining induction period, estimating shelf life, or determining the effectiveness of antioxidants. The second method is also used. It's called oil stability index. So what you do in this case, you get your oil, you put it in a container in an oil bath at 130 degrees C. So really high temperature there. And you bubble air into the oil sample. So you're basically giving it oxygen. So you bubble air, and then the volatiles are collected into a secondary flask. So volatiles, when oxidation happens, some volatiles will be produced, and they will be collected into another flask, and conductivity is measured. So when the conductivity changes, that gives you an onset of oxidation. Oxygen bomb, from the name, you have a chamber where you put your sample in it and you pressurize it by oxygen. And you take that chamber and you put it in boiling water. And you monitor drop in pressure. When you get an abrupt drop in pressure, that's an indication of an uptake of oxygen. So it's an indication of the start of oxidation.
Excuse me, Pam.
Yes?
Just to back up, oil stability index, you said 130 C oil bath, and you bubble air into your sample. This produces and collects volatiles, which changes the conductivity, which can be measured. Is that correct?
Yes. So basically, you have your flask where your sample is, and you have air bubbled into your sample, and then there is a connection between the sample flask to another flask where you have water, and you're measuring conductivity in that flask, and then the volatiles are they go from that one flask to the other when the oxidation starts occurring, and then the conductivity is measured in the other flask that had water.
Okay. Got it. Thank you.
Yep. Okay. So part of characterization of the oil, like we said at the very beginning of the lecture, is looking at the different components of the lipid. So you're looking at presence of free fatty acids, mono, di, and triacylglycerols, phospholipids, cholesterols, and lipid-soluble pigments and vitamins. So looking at these different components, it's part of characterizing your lipid. So a lot of the methods rely on GC methods, like we did for fatty acid composition. Also, cholesterol, you rely on GC method. You just have to derivatize cholesterol. And TLC method, thin layer chromatography, is done to kind of monitor qualitatively the presence of these different components. So for fatty acid composition, whether it is the different components of the fatty acids in the fat or the oil sample, we use the method that you've done in the lab with fatty acid methyl ester, the derivatization, saponification and derivatization of fatty acids into methyl esters. So it's used to determine composition, it's used to detect adulteration the way you did for olive oil adulteration. Now for cholesterol, cholesterol is an unsaponifiable matter. So when you saponify triglycerides, you're breaking the fatty acids esters from glycerol. Cholesterol is not saponifiable, so it won't saponify. So when you saponify with NaOH, let's say your triglycerides, you get fatty acid salts. So these fatty acid salts are soluble, then you can separate them and your cholesterol remain in the organic phase. So here you don't have methylation, so you don't methylate. You just saponify without presence of any methylating reagent. You just saponify, you get the salts of fatty acids that remain soluble, and the cholesterol is left behind in the organic phase, and then you take the cholesterol, you derivatize it, and then you can measure it by GC analysis. Okay. This is just an example of thin layer chromatography looking at different fractions of lipids. Here you have silica gel as the adsorbent, and then your mobile phase or eluting solvent is an organic phase. So what moves the most are the least polar. What resists moving along in the along with the organic solvent is the most polar. So you can see that phospholipids are the most polar lipids. So you see that they barely move. And then monoacylglycerol is polar, less polar than the phospholipids, but then the polarity decreases from phospholipid to monoacylglycerol, diacylglycerol, fatty acids, triglycerides, and so on. So you can run standards. These are the standards, and then your sample to determine what different components you have in your sample. Qualitative, you can do semi-quantitative detection by looking at band intensity, but this would be, if you need accurate quantification, then you need to do GC analysis. Okay, with that, we end fat characterization. Any questions? Now, we have 20 minutes to start protein separation and characterization. Another one of my favorites. Now you're going to wonder what's my least favorite, but I'm not going to tell you. Okay, so this chapter, we're going to talk about two different things, protein separation and protein characterization. Let's see here. All right. So separation of protein can be based on differences in solubility, adsorptivity, or denaturation. Any idea, based on what you know about proteins from food chemistry? Let's see, somebody just answered. F. Okay. Any other answers? G. I see more G's. Yes, so this G is a good guess. So proteins differ in so many different biochemical characteristics that we're going to talk about. Because they differ in certain biochemical characteristics, they are going to be different in solubility. They're going to be different in their net charge, in their hydrophobicity, in their different ionization, ionizable groups or functional groups. Therefore, they will have differences in adsorptivity, in their way they adsorb to surfaces. So they're also different, they have different denaturation temperatures. Different protein denatures or unfold or change from their native form at different temperatures, at different pH, under different solvents, organic solvents. So the difference in their denaturation among different proteins, we can allow us to separate them from each other. So how to do that, that's basically the topic of this chapter. So if we have proteins in a mixture of proteins in solution, what can we use out of these techniques to separate them? So I see F. And then I see G. Okay, I'm going to go with G. We're going to learn about separation based on different characteristics. So separation based on solubility can also involve salting out, because some proteins can remain soluble, let's say at 0.1 molar ammonium sulfate, let's say. But other proteins at 0.1 molar ammonium sulfate will precipitate. Why? Because protein A and protein B are different in their net charge. So some proteins at low salt concentration will precipitate, while others require a little higher salt concentration to precipitate. So we can separate them from a solution by salting out, by changing salt concentration. We can also separate them based on size using size exclusion chromatography. Electrophoresis, we're going to learn about electrophoresis. We can separate them in a gel based on size or based on charge to size ratio. So we can separate them to look at them differently, like to look at the different profile within a protein sample. But electrophoresis is not really used as a preparatory or preparative method. That means if I want to separate the protein and collect them for a different analysis, electrophoresis is rarely used for that purpose. Electrophoresis, it just tells me what different proteins I have in my sample, how different they are in molecular weight, or how different they are in charge, or how different they are in their isoelectric point. So it can give me differences in looking at different proteins within a sample. But only very rarely we use electrophoresis to kind of separate protein and take them for further analysis. And that we use it sometimes to do a mass analysis, like MALDI, that Gary talked about in his MS lecture. We use electrophoresis, and then we take the spot on the gel and we remove the protein from the gel and then run mass spectrometry to determine molecular weight and other characteristics. Okay. So this is just introducing, right? We're going to talk about all of this in detail. Now, before I talk about different protein separation, why do we care? That's kind of the theme question I always ask you. Why is it important, or why do we do protein separations? Why do we care about separating proteins from a mixture? Mixture of proteins. Yes. Okay. what I get here, protein functionality. Oftentimes I need to separate protein from a matrix or separate it from each other to assess their nutritional quality independent of each other, their functional properties independent of each other, or somebody said a protein powder or protein ingredient. In industry, they separate protein, they isolate protein, they purify them so that we have ingredients. We have isolates, we have concentrates, we have protein flour, and we use different methods of isolation to produce these different ingredients. Sometimes we isolate proteins and we purify them for certain assays. So enzymes, for example, they're proteins. So we separate enzymes from a starting material, let's say a microbial source or a plant source or an animal source. We isolate that protein to use it as an enzyme, a purified enzyme, or as a substrate in a reaction. So here we go for production of protein ingredients. To do further analysis, we isolate the protein and we determine its composition, amino acid composition, its tertiary structure, so we can characterize it better, understand its functionality, understand its biochemistry, understand its nutritional quality. To be used in an analytical assay, such as being an enzyme or an antibody, for instance, can be isolated and used, such as COVID antibody treatment. To determine impact of processing on changes in structure. So sometimes we run electrophoresis, let's say, which separates protein, to look at if certain processing caused polymerization of the protein. Denaturation, polymerization. So we run the same protein before processing and we run it on the gel after processing, and we see if we generated large molecular weight, which is an indication of polymerization. Sometimes it's desirable, sometimes it's not desirable. So proteins are fascinating molecules. They're very complex and they differ in so many different characteristics. So the protein composition, amino acid composition, amino acid sequence, protein structure will dictate nutritional quality. How? It's not just about amino acid composition and essential amino acid, but also about the structure of the protein and how digestible that protein is. So changes in protein or differences in protein amino acid composition and sequence and structure impact nutritional quality. It impacts functional properties and also the biochemical characteristics of the protein. So with biochemical characteristics, what do I mean? Biochemical characteristics are related to these characteristics. So size of the protein, the charge of the protein, which indicate their solubility, their thermal stability, how well they absorb the different matrices, and their affinity or their biological affinity to other molecules. So all of these characteristics are dependent on amino acid composition, sequence, and molecular structure. Because proteins are fascinating and complex and they differ in all of these characteristics, we can use any of these characteristics to separate them. And that's what we're going to talk about. How we're going to separate them based on differential solubility. So how they differ in solubility. Salting out is the first one here that I'm going to talk about. So in protein chemistry, you might have heard, or in your food chemistry class, you might have heard of something called salting in and salting out. So salting in, sometimes you add a little bit of a certain type of salt to enhance protein solubility. Basically, that salt adds a charge load to the protein, helps it interact with the water better. Sometimes certain salts, like ammonium sulfate at specific concentration, they shield the charge on the protein. They interact with the different charges on the protein, shielding the charge So now you don't have electrostatic repulsion between two protein molecules. The charges are shielded. So you have attraction via hydrophobic interaction. These proteins are going to come together and interact with each other because there's no longer repulsion of charges. And not only that, the salt is going to compete with interaction with water. So the protein is interacting less with water, so it interacts more with each other. They aggregate, they precipitate. All right. Again, this phenomena is dependent on the net charge of the protein. The more charge there is in the protein, the more salt you need to precipitate it. Okay. So here's a question for you. And I put it in a very simplistic manner. So you have 5 different proteins. They differ in their net charge. A has the least amount of charge and E has the highest number of net or highest net charge. How do I separate C? Think simplistically, don't give me numbers, just give me kind of like your approach. What would you do to separate C using salt? So it's 2-step separation. Yes, correct there. First high charge, then low charge. I lost you there, Sam. I got you at the beginning and then I lost you. How do I do that fractionation, Chrissy? So I have salt, I have protein in solution. I have a salt powder next to me, and I have protein in solution. Anastasia. Yeah, say that again. You slowly add the salt. Yes, so this is kind of the crude way. What Anastasia mean by slowly adding the salt. I will put salt at a specific concentration that will precipitate A and B, but leave C, D, and E in solution. So I will put just enough salt that makes sure that A and B will sediment when I centrifuge. And then now I have C, D, and E. Then I add a little bit more salt that I know will precipitate only C and leave DE in solution. So basically I play around with the salt concentration. Now you would go, how do I know how much to put in? Yes, you don't know that, you don't guess that. You basically need to know your proteins, the composition, their total net charge at a particular pH. Maybe somebody has published this work before you and there is a set concentration that is known. If not, and I'm sure now 100% it is known and published, but usually you would know what you have and try to calculate how much salt you need to block these charges, and you go from there. It's complex, it's not easy, but what I'm trying to tell you here is this, to learn the concept. The concept is I precipitate A and B, but at a specific salt concentration, make sure C, D, and E are in solution, then I add more salt to precipitate C. So it is a 2-step that, like Sam said, it is a 2-step fractionation. All right, proteins differ in their isoelectric point. If you want to separate casein from whey protein, you reduce the pH to 4.6. You get the curd and you get the whey, right? So you can separate whey protein from casein protein by precipitating at the isoelectric point of casein, which is a 4.6 isoelectric point, which means the protein at this point or this pH have 0 net charge. So they will interact with each other, the hydrophobic interaction, barely any repulsion, and you can separate them from different proteins that are soluble still at pH 4.6. Okay. You can precipitate protein out of solution by using organic solvent. So proteins are, if they are in aqueous solution, let's say you have protein in water and you have other solubles in there, and you just want to take out this protein and separate them from the solubles. So the protein in the presence of organic solvent, what will happen is the organic solvent will react with the surface of the protein, get charged, and it is an organic nonpolar solvent. So the organic or the nonpolar residues within the protein, in the inside of the protein, go out to the outside. So that means the protein unfolds because now there is acetone instead of water. So instead of hiding from water, they now expose themselves to the acetone. So the protein unfolds. The hydrophobic residues are exposed and the protein interact with each other via hydrophobic interaction and precipitate. Okay, so one example of this, if you have I think we talked about it in the carbohydrate lecture, where we had the 80% methanol, and you solubilize the oligosaccharides, protein will precipitate in the presence of the organic solvent. Protein denaturation, that means you can denature the protein, and once the protein is denatured, it will interact with other proteins in solution via hydrophobic and disulfide linkages, form polymers, and precipitate. So you can denature the protein. A lot of times this happens just to separate proteins. Let's say you have whey, which is a byproduct of cheese production, and you just want to precipitate whey protein out and use it as a nutritive additive in a product. You can simply heat it to over 72 degrees Celsius. Whey protein will denature. Both beta-lactoglobulin, alpha-lactalbumin, they all will denature and they will interact with each other and precipitate and separate from other components or solubles in whey, such as lactose and salts and other components. So a couple of minutes before we end, this is an example that is done in industry to separate, to produce soy protein concentrate and soy protein isolate. So two different ingredients. We get defatted soy flour. It's very important to start with a defatted flour before protein separation because the fat interferes in the separation because protein emulsifies with the fat and it's hard to separate it. So we remove the fat, we have a defatted flour. And if you want to produce just a concentrate, that means you want to remove the soluble sugars because in soy there is no starch. There's fiber, there's soluble sugars, there's protein, salts, and that's it. So we put aqueous alcohol, separate the solubles. In ethanol, let's say, we can separate oligodimonosaccharides, they get soluble, then you spin down the rest, you have the fiber and you have your protein. You get a product that is 65% protein. You can do this with alcohol or water wash, and you acidify the water to help protein precipitate and separate it from the soluble. You still get protein, insoluble fiber, and that's why you have 65% protein. And this product is good for extrusion to produce texturized protein product. Now, the isolate production, where protein concentration is above 90%, you take that defatted flour, you solubilize the protein at pH 7.5, 8, 8.5, alkaline pH. So the proteins and sugars and other soluble fibers are solubilized and insoluble fiber is precipitated. Now you have sugars and protein and soluble fiber, and you want just the protein. You acidify. That means you precipitate at the isoelectric point of this protein. 4.5 is the isoelectric point of soy. So you precipitate the protein and you throw out your soluble fiber, soluble sugars, some salts. So you have protein in the precipitate. You do a couple of washes, potentially, then you neutralize. You never want to leave the protein at its isoelectric point. It loses functionality. You neutralize it to pH 7, you spray dry, and you get an isolate of above 90%. Sometimes it's close to 95% even purity, especially for soy. So that's actually what's done in industry to produce these isolates and concentrates. All right, that's a good stop here for us. We will continue on Wednesday.